When we look at hydrocarbon reactions, we typically look at the physical properties of our individual hydrocarbons, such as our alkene functional group here, right? So we talk about the fact that our alkene double bond here is somewhat electron rich, and how we can act as then a nucleophile based on that electron density that we have there in our alkene double bond. Now, this of course is very important for a number of different organic reactions. However, this alkene can also affect our nearby sites. So when we have our alkene double bond with an adjacent carbon, we refer to this as our allylic carbon, and we call this our allylic group overall. Is anytime we have that alkene double bond and an additional adjacent carbon. So our alkene is going to influence the reactivity of that adjacent site. We see this with ions and radicals that form at that allylic carbon. So let's say we have a carbocation that forms at our allylic carbon. So that would look like this. This would be our allylic cation. Now, when we have a carbocation here, we can actually move our double bond to help to stabilize that carbocation. So we have our allylic carbocation. We can rearrange it to form our structure over here. So our charge can move from the right side to the left side. And of course, our hybrid structure here would be our double bond shared between our three carbons, and our positive charge is delocalized. And this leads to resonance delocalization of our charge and stabilization of our carbocation. So this will have a huge effect on the overall stability of that carbocation, where instead of being stuck with our missing octet and that full positive charge, we can spread that out and help to share that instability associated with that positive charge. Now, of course, if we look at this system using our valence bonding model, so we would have our three carbons, and each of our carbons is going to have three groups attached, right? So we have hydrogens attached to each of our carbons. And with those three different groups bonded to each carbon, that means that we'll have sp2 hybridization. So I'm going to represent that like this. So I have my sp2 orbitals coming out at 120-degree angles relative to each other. These will overlap to form my sigma valence bonds between my carbons. I would, of course, have hydrogens at my other bonding positions. And now, in addition to my sp2 orbitals, I would also have p orbitals sticking out above and below each of these carbons. Now, if I look at this initially, so all of my carbons look very similar, right? They all have these p orbitals. They can all sit next to each other, and these p orbitals can overlap. So we can get some overlap between each of these p orbitals, and so we refer to this as a conjugated system. So that conjugation refers to the fact that we have overlap between p orbitals on each of these carbons. Now, if we look at our Lewis structure over here with our bond line formula, so we only have one double bond, right? That double bond represents two electrons sitting in two of these p orbitals that are overlapping to form our pi bond. Now, of course, as we know from our hybrid structure, our resonance structure, that shows kind of our true state of the molecule, that double bond is actually shared between our 3 carbons, right? So that's represented here in our conjugated system, where we have overlap between our 3 carbons with their p orbitals, and so these 2 electrons can really bounce back and forth between any of these 3 p orbitals. Right, so our 2 electrons can move around between these 3 p orbitals, and so we can really think of all of these carbons as being kind of bonded together in this one large pi bond. So of course, I mean, we do still have that positive charge, right? We don't have as many electrons as we might like shared between our carbons, but it does make for this more stable conjugated system as we delocalize our charge and therefore stabilize that carbocation. We can see a very similar scenario occur if we have an allylic anion, right? So previously we had a positive charge that we could move back and forth between our carbon on the left and our carbon on the right. If we have an anion, which would be caused by a lone pair on one of our carbons, we can also move that anion back and forth between our 2 carbons. So if I move my electrons down here to form a double bond between my 2 carbons, I need to move this double bond out of the way to make room for my new bond. And that results in my double bond moving over to the right, and my negative charge moving over to the left. Again, I can represent this as a hybrid structure with a partial double bond and a negative charge and lone pair of electrons shared between my 3 carbons. Again, if I show my hydrogens, I'll still have my same 3 groups at each carbon. This is representing, as before, I'm going to have my electrons shared in this conjugated system between my 3 carbons. Right? So the only difference here is that I'll actually have 4 total electrons shared within my 3 p orbitals moving between my 3 carbons. Right? So again, I get the same overall effect. Stabilization of that charge due to my resonance delocalization. So I can say that overall, my charge gets stabilized at that allylic carbon, right? Whether it's positive charge or negative charge, I'm always stabilizing that charge through this conjugation effect and this sharing of my charges between my 3 carbons. Now let's look at a third scenario where we have a free radical at our allylic carbon. So again, we'd have our 3 carbons here with our double bond, and now we have our single free radical electron, which of course would be sitting in a p orbital on our carbon over here. Again, if I want to try to move my free radical around, so I bring my electron down here, I need a second electron in here in order to form my double bond. The other electron from this bond can go over to my other carbon on the left. And just like my positive charge or my negative charge, I can move my free radical electron back and forth between my carbon on the left and my carbon on the right. In the same way, this represents a double bond shared between my 3 carbons and a free radical electron that's also shared between my 3 carbons. Again, in my conjugated system, I have my electrons shared between my 3 p orbitals, right? So my carbons are conjugated. In this case, I have 3 electrons that can bounce back and forth between my 3 carbons. I stabilized the charge before. Now here, I have my stabilized radical. So in each of my 3 cases, I can stabilize it, again, through this conjugation effect. So it can be positive or negative charge, or it can be my free radical. All of these will be stabilized when they're next to my alkene as this allylic carbon. Now, of course, it's important to ask ourselves, what is the effect of this stabilized radical or stabilized charge, right? How does it impact our actual reactivity at that allylic carbon. Now, of course, the most basic case is acidity, right? So if we have an allylic carbon with our methyl carbon here with 3 hydrogens, and let's say we deprotonated it, so our hydrogen was pulled off, and we gave our electrons to our carbon, right? So this would be our allylic carbon reacting as an acid. We would produce an allylic anion, which now, again, as we said, is going to be stabilized by that delocalization and my conjugation. This means that if I compare the acidity of a propyl carbon, right, without my alkene double bond over here, and I was going to deprotonate this by reacting it as an acid to form my propyl anion over here, this would be much less stable than my allylic anion, which then means in turn that this is more acidic. Now, this isn't a huge difference in terms of our overall acidity. Our pKa for our normal propyl group is somewhere around 60, whereas my pKa here with my allylic group is around 40. Right? So pKa of 40 is still an extremely weak acid. Right? We would need a really strong base to deprotonate this. So it doesn't have a huge effect on our allylic carbon, but it does have a significant difference in our acidity overall. Now, the stabilization of our allylic cations has a much larger effect on the overall reactivity of our allylic groups. So in this alkyl halide here, we have our bromine, which of course can act as a leaving group, as we've seen in our discussion of nucleophilic substitution reactions, is attached to that allylic carbon. Right? So we have our bromine attached to our carbon right next to our alkene. Now, as we know, in a substitution reaction, a SN1 reaction, our bromine would come off as a leaving group, and it would produce our carbocation. Now, in this case here, our positively charged carbocation is right next to our alkene double bond, right? It's an allylic cation, and so we can again stabilize it using the resonance of our double bond. Our positive charge can move back and forth between those two locations. We again have our stabilized charge as we have those electrons getting shared in our conjugated system. What's the impact of this? Well, again, if we compare a similar alkyl halide, but without our allylic group, right, without our alkene double bond, this tertiary alkyl halide, right, normally we've seen that tertiary groups react quite quickly in a SN1 reaction because they form that somewhat more stable tertiary carbocation. This will react much slower compared to my allylic tertiary carbocation. So we see a slower reaction because even though we form that more stable tertiary carbocation, the stability of that tertiary carbocation is nowhere near as stable as my tertiary allylic carbocation. Now, it's not that our substitution effect doesn't play a role anymore, right? We still would prefer a tertiary carbocation to, say, a primary carbocation, even if it is an allylic carbocation. But if we have an allylic carbocation with a similar substitution pattern, it's going to react much more quickly compared to our tertiary carbocation. So this reaction would proceed more quickly. We would form our two carbocations, and we can then attack with whatever nucleophile we have to produce our final product. So if, say, we had a chloride ion present to act as a nucleophile, this could attack our allylic carbocation, and we would get our new product from our SN1 substitution reaction in a very rapid reaction. Now, of course, our resonance structure here represents also an alternative reactive site, right? So we have our carbocation moving back and forth, which means that alternatively, we could also attack this carbocation over here and produce an alternate product here with our chlorine at this primary position and our alkene double bond over here at our tertiary site. So this product would be a minor side product that would also form. It wouldn't be our major product because, again, we still prefer our more substituted carbocation. So even though both of these resonance structures exist, right, we can think of our carbocation as kind of bouncing back and forth between these two carbons. This will still be our major intermediate, right? This will be our major resonance contributor, and so this will be our major product. Now, if we rearrange our allylic alkyl halide to a primary alkyl halide, again attach that allylic carbon. So of course with primary alkyl halides we primarily go through SN2 reactions. And as it turns out, with this primary allylic alkyl halide we can still undergo an SN2 reaction. Even though we don't have the same carbocation intermediate, our allylic group will still speed up our reaction. So if we compare our primary allylic alkyl halide with a standard primary alkyl halide, we will again see the same effect where our primary alkyl halide will be much slower compared to our primary allylic alkyl halide. So now, of course, in this case, it's not due to that carbocation, since we don't have a carbocation intermediate, but our conjugation actually still helps to stabilize our transition state and will still speed up our reaction. So even though we don't actually form that full carbocation intermediate, we can still help to stabilize this transition as we go from our initial reactant to whatever our final product is. All right, so if I bring in a good nucleophile, like my sulfide anion, this would attack, and this would break off. In my transition state, so my transition state doesn't actually occur for any extended period of time, but as I'm kind of halfway through that reaction, my bromine is starting to break off while my sulfide is starting to attach, and I end up with a partial positive charge at that carbon, my allylic carbon, and this partial positive charge again is going to be stabilized by my conjugation. So even though I don't actually have a carbocation that forms, I can stabilize my transition state and speed up the reaction to my product. So again, with our primary alkyl halide without my allylic group, I would see that reaction still, but it would be much slower compared to that similar primary alkyl halide with my allylic alkene. The final scenario where we see a big difference in our reactivity based on our allylyl group is if we have a free radical reaction. So as we've seen, if we take an alkene and react it with our halogen, if we have light, it can break apart our diatomic halogen bond. So we'd have our homolytic cleavage to form our bromine radicals. And then these bromine radicals can react with an alkane. So our alkane allylic carbon here and we can produce an alkyl radical. Right? So we'd react here, and this would lead us to our allylic radical, which again, as we've seen, would be stabilized by this conjugation effect. So of course, anytime we have an intermediate that's stabilized, that indicates that our reaction will occur more quickly, right? If it's a more stable intermediate, this step will go more quickly to form that initial intermediate, and so our reaction overall will go more quickly. Of course, in this case, that free radical would go on to react with another unit of our diatomic bromine, and we would end up producing our allylic alkyl halide. Now, of course, the advantage here of our reaction is that now we have a specific reactive site, right? Our radical really wants to be next to that alkene where it can be stabilized by this conjugation effect and that resonance delocalization. Remember, one of the problems that we've had with our alkane halogenation reactions is that they're not all that selective, right? You can have multiple sites where they might want to react. Right, so we talked about before with hexane, we have multiple identical sites where we could add on our halogen. Right, our halogen prefers more substituted sites, but we have 4 sites here with equal substitution. Now, if I have an alkene double bond, now I'm going to prefer to add on my halogen right next to that alkene double bond. Right, so now my preferred site would be right here, where I'd have that stabilized radical, and I would then end up substituting my bromine on near my alkene. Now, one thing you might notice here, right, is that we have an alkene here, and we're adding a halogen. Right, so why can our halogen just react directly with our alkene? So as we've seen, we can have our halogenation reaction where our alkene attacks the halogen as a nucleophile, our halogen attacks back, and we end up forming this cyclic colonium ion. To resolve this problem, we're going to use a source of bromine that can't directly react with our alkene in this halogenation reaction. So this is our N-bromosuccinimide. So we have a 5-membered ring system with a nitrogen attached to our bromine. And then we have 2 carbonyl carbon-oxygen double bonds on our ring system as well. So this is our N-bromosuccinimide, abbreviated as NBS. NBS essentially acts as a source of bromine. Right, so this nitrogen bromide bond can be broken relatively easily. And so this will produce our diatomic bromine eventually, but in relatively small amounts. And so if we have our peroxide present to help produce radicals, in addition to our NBS, we can just produce enough bromine to get our radical halogenation without actually reacting through our normal alkene addition halogenation reaction as well. So if we take our NBS and react it with our allylic carbon here, our NBS again will act as our source of bromine that won't allow for a normal alkene halogenation reaction, and we'll get our allylic alkyl halide produced as our primary product without any of that of our halogenation products interfering. So through these different reactions, we've seen how this conjugated system here can have a large effect on the reactivity of those carbons adjacent to our alkene. Now moving forward, we'll start to look at larger conjugated systems. Right? So right now we have, in our allylic system, we have 3 carbons, each with their p orbitals overlapping, forming this pi bonding system across the 3 carbons. if we add another carbon, so if I take off my hydrogen here and attach one last carbon over here, so now I have another p orbital, and this p orbital can still overlap, right? So at this point now I can have two different double bonds, right? So I have two pairs of electrons essentially representing two different double bonds. So I can represent these two different double bonds using a bond line formula like this. We would call this a diene, since we have two different alkene bonds. Since all of our p orbitals can sit next to each other and overlap, we refer to this as a conjugated diene. Now again, since all of these can overlap with each other, essentially making one large pi bond, we can't really think of these just as two separate alkenes, but really they're going to be connected to each other and they'll affect each other's behavior, similar to how our alkene affects the behavior of our allylic carbon. So this will be one of the topics that we'll look into next.